Okay, yes. Okay, this is the sixth workshop we are doing in this working group 8 of Landwehr. So the working group 8 is about IoT-based monitoring and warning, and this workshop is about real-time monitoring using IoT technologies. This is a joint workshop between Landwehr Working Group 8 and also the EU project, the HUT. The reason is because there are many partners that are both involved in these, in Landwehr, in this working group, and also in the EU project, the HUT. For these reasons, there is Michele Calvello, who is both the president of Landwehr and also the coordinator of this EU project. First of all, a few slides about what is Landwehr. Is an international network on landslide early warning systems. Is multidisciplinary. Is a no-profit network of people, basically, who are interested in cooperating for addressing and promoting issues related with landslide early warning systems. At the moment, there are these 5 working group operational. Others have been terminated. So there is working group 3 is about communication with stakeholders. 4 is about e-learning. 5 innovation. Working group 7 operational national landslide early warning systems. And then this working group 8, is about IoT-based monitoring and warning. So real-time monitoring and slope stability analysis. If you want to know more, please visit the website here. You can register, it's for free. And if you register, you can be informed about initiatives, activities, and you can receive the newsletters to stay updated and join the activities. What we are going to do in this working group, what's the main aim? Is promote the application of innovative and traditional sensors in using Internet of Things technology, and then share experience about real-time monitoring and modeling. And then we would like also to show and to present case studies. And this workshop is going in actually in this direction. So just three bullet points that I want to summarize here. So what we are going to do and what we will do in the upcoming months is informing and sharing information about knowledge on IoT-based monitoring and warning among the partners of Landwehr and the Working Group 8, being informed of what's going on about IoT-based monitoring and warning, case studies and initiatives. And then the last point is what we are working also together with the HUT is creating a monitoring and warning catalog of sites of case studies that are providing real-time monitoring and or IoT-based warning too. And then we want to make this data set available, but not in real time. So it's to kind of create an encyclopedia of case studies that are using IoT technologies and for several purposes and make this data available. We are planning to do that perhaps using Zenodo. Let's see. So if you want to be part of this, please go on the Landwehr website, subscribe, and then you will be updated and involved in this project too. This is the agenda for today. I already have taken too much time. Then there is Flavio Alexander Azusa Belis and Francis Nieto. So the first is from the UPC, University Politecnica Catalunya, and then the second is Arantec. They're going to make a joint presentation. Then there is Minu Abram from NGI, she's here, and then Marius Angelopoulos from British Geological Survey. Before that, as I said, this is a joint workshop between Landwehr Working Group 8 and the HUT. To tell you what is the HUT, there is Michele Calvello. Please, you can unmute yourself and say few words about the HUT EU project.
Thank you, Luca. I'll be brief, and I excuse myself in advance because soon after this very, very brief presentation, I have to leave because indeed I have another meeting at the same time. They are waiting for me also there. So as Luca was mentioning, the hut is, and many of you are in the project. You know it if you are in, you don't know it maybe if you are not in the project. It's a cooperative project funded by Horizon Europe. We have a consortium of 26 partners. You can see the website here. The hut stands for the Human Technology Nexus. And the other subtitle is Building a Safe Haven to Cope with Climate Extremes. In the project, it has a duration of 4 years. We started in October 2022, so we still have 2.5 years to go. We are not only focusing on landslides. Landslides are one of the many so-called climate extremes. We are using the jargon that is used by the European Commission. And we will focus on all of them at once, trying to promote best sets of tools, risk management tools and approaches that maybe already are working for some of these risks and then can be transferred to others. So our approach in the idea, you can see here a slide where there is a picture that comes from the proposal. Now we have new way of formalizing the visuals for that. But anyway, the idea is to have transdisciplinary work. Of course, we are doing something in that project with some of the people that are part of the landslide risk community, not only landslide early warning systems. And I can say that some of the case studies are, and what you will be seeing today, comes from partners of the project. Next slide, please. Thank you, Luca. The arena where we play, where we are testing solutions, where we are developing solutions, is 10 demonstrators scattered around Europe. We go from, where I come from, southern Italy, demonstrator number 3, Lattari Mountains, to Iceland. I see somebody from that demonstrator today connected, and also others. In relation to landslides, the main sites, locations, and people indeed are, as in Salerno, the people from Iceland. We have Dorset in UK. We have Bern in Switzerland, and we also have, and they will talk today, people from UPC and from Adantec dealing with landslide risk and flood risk in the Pyrenees Mountains. Next and final slide, the new visuals for the 6 climate events are those. So like landslides, you can see they are there in green, landslides, debris flows, all included. And then the idea is, again, to have mixed transdisciplinary work within the project. Today, this seminar, I thank you, Luca, for that, for this initiative, will be something that is definitely framed within Landaware, but also in the hut, the work package that is dealing with these activities is the work package called Science and Technology, where we have a specific monitoring and modeling tasks. So thank you, Luca, for the initiative, and I'm very sorry I cannot stay connected today. So please excuse me for that. Anyway, there is the recording, so I will listen to you.
Yeah, thank you, Michele. This is what I was saying. You can watch the recordings afterwards. But thank you very much for this for describing the hut project. So this is the agenda for today. I think we have done with the introduction and by Michele, and then we can start. So we can start with these 3 presentations of roughly circa 20 minutes each, and then we can have a discussion and questions, curiosities. And in the discussion, you can also tell me if you are interested in kind of share your data or your monitoring case study if you have one. Okay, Alex, please unmute yourself, share your screen, and okay. This virtual floor is yours.
Can you see my screen? Can you see my screen, right?
Yes.
Yes.
Okay. Well, good afternoon, everyone. First of all, thank you, Luca, for the invitation. I am Alexa Sursa. I'm currently a second-year PhD student in UPC Barcelona. And this presentation, I want to introduce to you the preliminary results of this multi-hazard model that we are developing in the Aran Valley, located in the north of Barcelona. Today, my colleague Francis and I will try to be brief, summarizing our main results. What is our motivation? Well, our study area, located in the Garona River Basin in the north part of Catalonia, was severely affected by a cascading event, flood landslide event in 2013. As you can see, there was the devastating event in which there were a lot of economical losses, around 100 million euros. Which is particular in this event was the snow melting contribution was really important to make the disaster even worse. So previously, after the event, there was some studies that were carried out. All of them were focused in different fields, in the hydrological component, geomorphological analysis, landslide model, climate change scenarios, but any of them tried to integrate all of this in one study, which is our main objective in our demonstrator. It's developed a prototype early warning system by performing a multi-hazard modeling. Specifically, we want to propose a fast and reliable couple model, and also in parallel develop a data portal to share all the information which the model is providing in a real time. So our general workflow have two main components. The first, in which UPC is more involved with the modeling, and the second company is more in charge of Arantech, the monitoring. In the modeling, we are working in a period of time of 10 years from 2010 to 2020, mostly working with the precipitation and temperature. So we are considering in the multi-hazard modeling four main components, or three main components: the snow, the hydrology, and the landslides, considering the initiation areas and the runout areas. In the monitoring component, we're working with more variables and real-time monitoring of precipitation, temperature, discharge, and also soil moisture. So we are trying in the end to build a data portal website in which we will share all this information, in where all the multi-hazard warnings will be shared, and which in combination with exposure data, we are trying to provide an impact-based early warning system in the end. So we go in deep with the couple modeling component. We're working in three main models. As I mentioned, the event in the Aran Valley was very impacted by the snow melting, so we had to consider a snow model. The snow model that we decided to use is the Snow 17, a model developed in the US, which basically need only temperature and precipitation data. So based on a temperature threshold, we can differentiate the precipitation into components in snow and in rainfall. So the model internally modeled the snowpack contribution, considering the snow water equivalent in the snow melt. So the main output of this snow model is a combination of rain plus melt, which later on is used as a main input for the hydrological model, CREST, which is also developed in US. And this hydrological model performs all the hydrological cycle in basically three reservoirs, one which simulate a soil layer, and two other ones, to simulate a fast flow and a slow flow component of the hydrograph. So in the end, we can get the discharge time series, and also it provides a simple module of to simulate the flood extent. So the main output of the hydrological model then is used in the landslide model. These outputs, the more important one are the infiltration and soil moisture, which later, based on the infinity slope theory, we can calculate the probability of failure map, the initiation areas, landslide initiation areas in our study area. So these preliminary results, we check first the snow modeling. We actually now can identify and see which is the temporal and spatial variation of the snow. In this case, I'm presenting here the snow melt component from the Snow 17 model. We can understand a bit better that this is something that in the previous studies, they didn't do it, which was the progress that during the week of the event. In this case, you can see how the water was being melting during this week. And how we validate these results? Well, we have some stations and we have data of the snow water equivalent. So specifically for this station and for this period in 2012, in the hydrological year of 2012 and 2013 in the Bonnet station, you can see that the model is actually representing very well the pattern, the time pattern. And also now we can understand better the process of snow and melting at the same time. Regarding the hydrological modeling, we have some stations also, discharge stations. This is Bossos is the most downstream station located almost in the outlet of the basin. So we see that again, statistically, we are getting good results, and also we are still validating the flood extent, which the model, hydrological model, is also providing. This is a bit challenging as there is no. It's hard to find image, a satellite image specifically for the day of the event. So we are basically trying to validate these maps based on pictures that we have during the day of the disaster. Related to the landslide, so as I mentioned, we use the outputs results of the crest to fit our landslide model. So basically taking infiltration and soil moisture, we can simulate chronologically the susceptibility maps from each day. So far we are getting results that are providing, they're actually matching well with the landslide inventory that we have for the day of the event. And also we are preliminary results of simulating the runout areas of the initiation areas using a Monte Carlo approach. Well, the aim, as I mentioned in the very beginning, is to propose a prototype early warning system. We are now working in the multi-hazard modeling, but the general panorama of this all these studies to provide this schema I'm showing right now, we can say that we have three main components in this preliminary early warning system. The first one related to the data collection, which is mostly Arantec is working in this. Francis will explain a bit better later. And we are working from now in an Amazon service. So the main idea is provide us forecasting variables that are so far will be taken from MeteoBlue platform, which every 24 hours this scheme will be run. So we'll perform a multi-hazard modeling that we're still working on, and lately it will provide a warning emission. We are currently trying to automatize all this process. We already finished, let's say, this first component. We already have it automatized. We are still working here because, as I show you, what I mentioned was only preliminary results, and we're still trying to improve our results. But this is the main idea in the end. Well, now Francis may continue explaining related to the monitoring company.
Hi, everybody. Thanks, Alex, to introduce me, and thanks, Luca, to invite us to this presentation. Could you go back, Alex, please, to the previous slide? Yeah, here, as Alex explained, the first module of the prototype of early warning system consists in the data collection. the Arantec take care of this work, and what we have done is to collect the data of the same points that the model was trained with MeteoBlue, and we create a script to share this data in the format that the model could admit it and to run. Could you change? Could you thanks. Related to the IoT monitoring, we had different conversations to amplify the coverage in the region with volumetric water content sensors, and we decided to use two types of devices. The first type that is primed with the a yellow triangle, contains just the volumetric water content and their sensor, and its main goal is to have this soil moisture to correlate this information with the already installed stations and try to connect the rain and humidity with the soil moisture. The second type has another goal, that is to cover the regions that are ungauged, and we also have the rain gauge in this type of devices. Could you change the
Next slide.
Next slide, please? As we could see, the device, the volumetric water content sensor, is from the meter group. It's a Teros 10 that has a range until 70% of the volumetric water content and a good accuracy and resolution. Next slide, please. And the tail sensor is from Rika, that has a wide range and good resolution too. And the node that we have installed use LoRa communication and use photovoltaic system as power supply. And this node take measures every hour and send to our platform. Next slide. Here we can see a complete example of the installation of type 1 of device. We must to make a little hole in the soil and put the volumetric water content, and we try to use existing installations to install the node and the tier sensor. Could you next slide, please? From devices of type 2, we only had installed one because there are snow in the region that I showed before, but we are near to have all installed. The only addition of the previous type of sensor is the rain gauge. It's a panoramic that has self-empty and good accuracy, and it's good for this task. Next slide. Here we have another example of this installation, and next slide. And here we have an example of the dashboard of of the data that we collect. And as you can see, it works because we could see some relation with among the rain and the soil moisture.
Next.
Next, yeah.
Okay. Well, this is basically all we wanted to share so far. We can say that in terms of the modeling component, we were able to build a fast and reliable model. It takes around 5 seconds to run these first components of the snow hydrological in last night initiation. The statistical performance was proof that it's good enough. And well, now, as I mentioned, also we are trying to implement an hourly time step model, because so far we were working in a daily time step, and to improve the process automation of the prototype early warning system. Well, related to the monitoring, which is taken from Nanotech, as Francis showed, we already installed, if I'm not wrong, some new sensors. We are planning to install new ones to cover the remote areas in which we didn't have any sensor installed before. And the data portal also, so far is basic. We are taking all the information from the local meteorological network, if I'm not wrong. That will be complemented later on with the new sensor that Nanotech is installing. And I think also from the MeteoBlue platform in terms of forecasting. So that's all from our side. Thank you for your attention.
Thank you.
Thank you very much for your presentation. We can go forward with the next two speakers, and then we can so save your questions, write them down. You can also write them down in the chat, and then we can make these questions to the speakers in the discussion session at the end. So now it's Minu, it's your presentation. Do you want to present from here? No, system. Yeah.
Okay, so hello everyone. First of all, thank you, Luca, for this opportunity. So myself, Minu. I work at NGI in the Instrumentation and Live Monitoring Division. So here I would like to present a completed case study on operational landslide forecasting on a local scale, and a preliminary results of what we are planning to do on a regional scale. So let us just recap a bit on the early warning system definition. I know that the group is very informed, so just a fast recap. So when we say early warning system, we talk about a device, system, or set of capacities that generates and disseminates timely and meaningful information. And when we talk about landslide early warning system, this is an early warning system that is devoted to landslides. So coming to the components of early warning system, we have narrowed it down to the setting, modeling, warning, and response. If we look the components in detail, so in the setting, we define the type of landslide and the choice about the monitoring instrumentation and the strategy that we have to choose. And then in the warning model, we have both modeling and warning, and then we have to plan the response. So this entire setup constitutes an LEWS. But here we are going to talk about monitoring, modeling, forecasting, and warning. That is the major part of the warning model of an LEWS. So we are not talking about the complete LEWS, but mostly on the warning model and the forecasting scheme that we plan to implement. So this is a local scale case study that we had in Norway. So the aim of this study is the use of real-time hydrological monitoring and the publicly available meteorological data and hydrological and numerical modeling to develop data-driven models to forecast the stability of a slope. So we all know that many LEWS conventionally has been based on rainfall thresholds, especially when we are talking about rainfall-induced landslides. So they are based on rainfall thresholds or displacement monitoring, like inclinometers and other displacement monitoring. But here we only have hydrological monitoring, and we are trying to make use of the hydrological monitoring. We are not monitoring a slope that is moving, where we have actual movement. This slope has never failed. So we are monitoring a stable slope that has not failed so far. So we are using hydrological monitoring, and you can see the slope over here. It's very steep from the top. And when we come to the IoT-based local landslide early warning system, we have monitoring, modeling, forecasting, warning, and response, and we are not talking the response part here. We are monitoring the volumetric moisture content and the pore water pressure. Also, we are using rainfall, temperature, and snow depth and other meteorological parameters to get the forecast of the factor of safety of the slope. This is what we are trying to do. So when we have these data, we use a hydrological coupled with slope stability analysis as a physics-based model, and then we try to bypass it using a machine learning-based model so that we can implement this in real time in a completely automated workflow. So this is our IoT structure. We use the publicly available data from OpenMeteo API and the Norwegian Meteorological Institute, and we fetch the data via APIs, and this data is used into our digital twin model, which is a proxy machine learning based model, which is the proxy that we use for the physics based model. So we also get the real-time monitoring data from the sensors that we have installed. I'll get to more details of how we have installed the sensors. And this data is also being supplied to a common dashboard, which is called NGI Live. It's a data platform by NGI. So this will have the ability to fetch the data, then do the calculation, and also fetch the results back to the same platform. So this is NGI Live, where we collect all the data from the data loggers, we combine it, and then we display it everything together in the same dashboard. And for the implementation of this work, we use Azure functions. So the code that we have to forecast the factor of safety, it will be automatically triggered once in a day using Azure function. It's a time trigger that we activate at midnight every day. And when we change the code, it will get automatically updated using a pipeline. So this is the site that I have shown you before. So this is a well-characterized site where we can characterize 3 different layers of soil. And we also had the monitored volumetric moisture current measurements from which we can plot the SWCCs. So this is how we have installed the sensors. So on the top, we can see that there is a sandy silt layer, below which there's a clay silt layer, and then there is marine clay. But we are focused on this top layer, the top unsaturated layer, where we were actually getting the weakest slip surfaces. So somewhere here. So we are using all these volumetric moisture content sensors, which are installed, and the first pore pressure sensor that is installed. So we are not concerned about the depth below this. And here we have some additional sensors, but these were installed late in 2022. So we have not used the data because our database consists. We needed the data for a long period. So we used only the sensors which were available for a longer duration of time. So this is the data loggers installed at the site. So we did the numerical modeling in GeoStudio with the combined CFW plus StopW modeling. We did this modeling for different 5-year data, different 1-year data sets, 5 different 1-year data sets. So we have modeled all the 3 layers, and we had the monitoring data, the real-time monitoring data for quality control. So we used the monitoring data for back analysis. So this validation was carried out using Taylor's diagram, where we measured the correlation coefficient, the normalized standard deviation, and the mean square difference. And then we used the Taylor's diagram to find the optimum model that represents closely to the real world scenario. So once we have calibrated the model, we have also done a sensitivity analysis to find the best fit model. So this model now has the monitoring data, and the factor of safety outputs, along with the rainfall and temperature data. So this data was then used to predict the factor of safety. So the dependent variable here are the monitoring data, the volumetric moisture content, and the pore water pressure, and the independent variable that we are trying to predict is the factor of safety. You can see that the critical slip surfaces are along here, and it varies with time, but it's almost within the first top 6 meters. And the factor of safety also varies with time. If you see the different data sets that we have 5 different 1-year data sets, one for 2019-2020. The date starts from June 1st. So June to June, 1-year data sets. So if you can see, there is a trend of factor of safety depending upon the seasons. And we have used these parameters, the precipitation, which is rainfall plus snowfall, then the air temperature, solar radiation, relative humidity, wind speed, snow depth, and the albedo values. And for vegetation, we have used leaf area index, root depth, and vegetation height. So we also have the 2 future scenarios for which the rainfall data was available from the Norwegian Climate Service. Then it's very difficult to implement the GeoStudio itself within the automated real-time warning system. So that's why we wanted to use a simpler model that runs quite fast. So we tried to bypass this using a machine learning model. So we divided the data set into 3 different groups, where we use 4 of the data sets, 4-year data sets to train the model, and we use 1 for the validation. So we prepared 3 different sets, and we used different machine learning approaches, starting from the basic linear regression to advanced models like Bayesian-Ridge and MLP and random forest. And we have used all the 6 volumetric moisture content, the pore water pressure, the air temperature, and the leaf area index as the features to predict the factor of safety value. So here we started with other variables also. We did minor sensitivity analysis, and we ended up choosing these as the important features to predict factor of safety. So these are the results for the 3 different data sets that we have. So we decided to choose polynomial regression and random forest. Polynomial regression was performing better with the group 3, and random forest with group 1. The challenge that we had with random forest is it's performing well when the data is within the range that it has seen before in the training data, but it's not performing well when it has not seen this range of data before. So that's why we also wanted to use polynomial regression so that we can compare the results of both the models. So now we have trained a model with factor of safety. We know the features, and we can get the forecasted meteorological data, the temperature, and leaf area index is used as a rectangular function for which we have values when there are leaves, and then when there is no leaves, the value is 0. And still we need to predict the factor of safety. We have the forecasted temperature value, but we don't have the forecasted value for the volumetric moisture content and the pore water pressure. So this was tricky. So we had to forecast these variables. So this was carried out using pastas. This is a hydrological model which is based on the transfer function, and it tried to explain the observed time series. In this case, the hydrological variables that we are trying to predict, the volumetric moisture content and the pore water pressure, by one or more of the observed time series. So we tried to use the same input variables as we used in the physics-based model to predict the volumetric moisture content. So we use precipitation, temperature, solar radiation, leaf area index, relative humidity, wind speed, snow depth, and albedo. We did not use the vegetation height and root depth, which were constant in the physics-based model. So everything that was variable in the physics-based model was used here again to predict the forecasted values of the volumetric moisture content and pore water pressure. So these are the results of FASTAs for one particular day. So we can see that almost all of the predictions were having good agreement with what was observed, with R-square value more than 8 for all the models. Sometimes they are very close, 0.99. And then let's just recap what I have said so far. So we fetched the data, publicly available data from OpenVideo and MetNorway. One is not up and the other variables. And we also have the monitored data and the past publicly available meteorological data. All these data, along with solar radiation, leaf area index, and albedo, are fed to FASTAs. Now this will forecast the 3-day volumetric moisture content and pore water pressure. And this, along with the leaf area index and air temperature, will be used to predict the factor of safety using the pre-trained data-driven models. So this is the workflow. And here we can see the final product. It's available in the dashboard. So maybe I can show you the video. The video is a bit. So this is the dashboard. You can see the site, the location of sensors, and the cross section, and the predicted values for each day. The predicted factor of safety values for each day, and if the factor of safety value goes less than 1.5, then we get SMS and email alerts. So this is how we have defined, and this is how where you see the standardized volumetric moisture content, and also the time series plots for the predicted factor of safety values. And here you plot this along with what was observed, so you can have an immediate quality control. If the values are far away from what you have been observing, so then there is something wrong, so you have to check the model. And this is a regional scale case study that we are planning to do. This is for Kvam, again in Norway. So if you look at this site, this is located in the Innlandet County of Norway. And this is a site where we had major landslide events in 2008, 11, and 13. And we have the pre and post topographical maps, the DEMs, for 2011 and 13 events. So there has been many studies already on this particular site. And this is a good event to do a back analysis, since we already have good quality data, but we don't have a very good quality data for the soil properties. So we have to understand the here the only monitored data that we can observe is the groundwater table variation. So this has to be understood how the groundwater table is fluctuating, and we have to calibrate the material properties, especially the shear strength properties and hydraulic properties, using the 2011 event. And we have to test the performance of this calibrated properties using the 13 event. And then we have to employ these values in the proposed model. And this is planned to be done using the trigress model. I hope that every one of you are familiar with the trigress model. So this was developed by USGS, and we are using and further developed by CNR, IRPA, and other collaborators for a probabilistic model where we can vary the input parameters in a probabilistic way using a Gaussian distribution or a uniform distribution. So these are the preliminary results that we have observed for 2011 even. This is not a calibrated model. We are still working on the calibration. So the objective is to use this model, calibrate it well, and then validate using the second event. and then enable and implement this workflow in real time, where we use triggers. The main input for the triggers model is the elevation and the material properties, again soil thickness, initial groundwater table, initial infiltration rate, and the rainfall data. So these data will be fetched from API. The elevation data should be updated in case of a slope failure. And we are planning to save the model infiltration rate, which can be the initial infiltration rate for the next day run. So we are planning to do this on for every 24 hours, but with predictions made for every 1 hour. So this is so far planned, and this is the architecture that we propose for this model. We are doing modeling, forecasting, and warning, but unlike the case of the local scale study, we do not have very well instrumentation here for immediate quality control. And this requires a different set of API. That instead of having a single time series value, we have to ingest a map layer via API. So that's an digital infrastructure change that we are working on. And to conclude, the local scale study, the initial steps is already published. You can see the manuscript there, and the second step has been submitted. It's under review currently. So this is an approach to define IoT-based digital twin and to start the local LAWS, the basic components of LAWS. And it also shows the importance of how to calculate and validate a model using hydrological condition, and how can we use hydrological conditions to forecast the factor of safety. And this is very easy to adopt and implement in other slopes. And we have successfully automated the entire procedure considering both climatic meteorological parameters and the monitored data. And the regional scale, this is an attempt to automate a physics-based model in real time, because in the previous case, we have used a proxy machine learning-based model, but we are trying to automate a completely physics-based model for real-time forecasting. And we still have to calibrate the shear and hydraulic parameters based on the past observations. And this should be completely run within the cloud service. Here we have some certain challenges, and we are trying to overcome this. Yeah. So these are the references, and thank you.
Thank you, Mino. Again, we can either start writing questions or curiosity in the chat, and then we will read them later in the discussion section. I would rather go forward with the last speaker, and then we can have a joint discussion. Marius, please.
Hi, Luca. Let me share my screen. So good afternoon, Luca. Good afternoon, everyone. Many thanks for the invitation. I'm Marios Angelopoulos. I'm a professor of network and sensing systems at Bournemouth University. However, in the context of the HAT project, I am part of the BGS team, in the sense that I'm subcontracting, providing support with the IoT engineering aspects of our work. So today I will speak about key underpinning technologies for developing IoT systems, and I will also present very briefly our work in deploying such systems in the area of Dorset in the UK, and multiple instances, iterations over the years, and by doing so, I will provide hopefully insights on how the design, the development of the system matures over time. So I will begin with IoT technologies. I reckon that given the focus of this working group, many of you will already be familiar with. So hopefully my presentation will help provide some new context depending on your background. So firstly, during my collaboration with the BGS in this interdisciplinary topic, I realized that there is a perhaps disambiguity and ambiguity regarding the term of Internet of Things. What is IoT? The formal definition, as taken from the Oxford Learners Dictionaries, is a paradigm, a networking computing paradigm that provisions the connection of devices within everyday objects via the internet, enabling them to share data. So one may ask themselves that, okay, this is about machines generating and exchanging data. What is so special about it? So the key defining or differentiating characteristics of an IoT system and IoT devices are firstly the small physical form factor of the device. We're considering highly embedded systems that can either be integrated in the context of objects or broader artifacts or standalone IoT devices. The second characteristic is that we're considering them to be low cost, therefore being easy to provision, deploy, and operate. Secondly, they are ultra low power devices and systems, typically battery operated, and they can run over extended periods of time operating on batteries, and they, in order to do so, in order to have an extended lifetime, they operate at low duty cycles, operating autonomously. And all these combined, they allow the easy and unmasked deployment of such devices over an area of interest in the scope of what we're discussing today in order to monitor the natural environment. Now, these characteristics clearly differentiate such systems from typical computing systems and dictate the use of specialized technologies. So in the following, I will discuss about ultra low power microcontrollers, low powered wide area network communication technologies, and specialized cloud services. So I will begin from the hardware, the sensors. In general, a sensor is an electronic device that interacts with signals or captures signals from the ambient environment and are able to generate corresponding data. Such devices, sensors, can be grouped in two categories: passive sensors that detect signals without the need for dedicated power supply. They're typically a type of resistor or diode, for instance, temperature sensors, and active sensors that require a form of power source in order to function, for instance, laser ranging sensors or cameras. IoT sensors function through physical contact, radiation, or electromagnetic fields. Typically, whereas this is not strictly speaking, IoT sensors are usually not graded for industrial or scientific use, and this also relates to them being low cost and widely available devices. So whereas we have sensing devices and artifacts that may be very elaborate and sophisticated and used in specialized environments such as production lines, factory floors, and so on. When we're provisioning the deployment of sensors in use cases such as monitoring the natural environment, we're usually dealing with sensors that are not scientifically or industrially graded. There is a plethora of modules available on the market of the self-components that initially were developed for at-home projects, aiming at hobbyists, but of course, as technology advances, these are becoming more and more sophisticated. So selecting the appropriate modules requires a solid understanding of the sensory modality and the use case understudy, as well as the technical specifications of the sensor. So whereas there is an easy access to such systems, to such components, one needs to have some level of understanding, both from the use case side as well as from the technical side of things. So sensors are used in conjunction with IoT development platforms that are in order to form sensing devices. Development platforms are integrated microcontroller boards, such as those by Arduino, SparkFun, or Adafruit. They are low-powered constrained microcomputers which run on firmware rather than full-stack operating systems. So, for instance, personally, I considering a Raspberry Pi that is able to run on a full-stack Linux-like operating system lies on the fringe of IoT. I wouldn't consider it to be in the core of IoT. These boards, they have integrated wireless communication capabilities, typically Wi-Fi, Bluetooth Low Energy, and more recently LoRaWAN, NB-IoT, and other relevant technologies. They support multiple hardware interfaces, and therefore they can accommodate being interfaced with a variety of sensors and by using several hardware communication protocols, such as SPI and I2C. And in order to use them in developing devices, there is a requirement to know about their development environments, their IDEs, and basic electronics. So with regards to wireless communication technologies, before discussing the ones focused on IoT systems, I would like to have an overview of the ecosystem, of the broader ecosystem of wireless communication technologies. So on this figure, the horizontal axis shows the communication range, the typical communication range of each corresponding technology, whereas the vertical axis captures the supported baud rates, what we colloquially refer to as the speed of the network. Most of us are already familiar with personal or local area networks, such as Wi-Fi and Bluetooth, who over rather short distances are able to provide sufficiently high baud rates. In the same category, but supporting lower baud rates, but at a much more energy efficient way, lie technologies such as Zigbee and Bluetooth Low Energy, and these have been used mainly in the context of building automation systems. And for longer communication, we have the wide area networks, particularly the cellular networks, that are able to provide sufficiently high baud rates over longer ranges. These operate in the so-called licensed spectra. This means that the operator of the network pays a premium, pays a license in order to be able to use a dedicated slice of the spectrum, and therefore the end users also need to pay a premium, a subscription. Whereas the technologies I referred to earlier, they operate in the ISM band that is free to access. And over the recent years, LP1 low power wide area networks have been introduced that shifted the paradigm of how IoT systems are being developed. LP1s are technologies that balance the trade-off between communication range and power consumption. They are able to, they enable systems to transmit few bits of data over very long distances. They do so by using low frequencies to transmit the signal that allows them to achieve long communication range at very low bit rates, and they counter the low power, low frequency issue of being susceptible to interference from other sources by using sophisticated signal modulation techniques, such as the chirp spread spectrum in LoRa. There are LP1s that operate both at the licensed and unlicensed spectra. And the choice of technology depends on the particular use case requirements and coincidental conditions. For instance, if there is area coverage by a certain technology in the area of interest. This is a typical reference architecture of an LP1. So end devices, they are able to transmit data to access points that lie in their vicinity. And the access points are dual stack devices in the sense that they provide backhaul communication to a network server, which is a common characteristic of all LP1 technologies. So the access point and the network server are managed and provisioned by the network provider, who can either be a company or one can deploy their own infrastructure. And then the network server provides connection points to the application server, which can be Microsoft Azure, AWS, or a custom application server that will host the visualization dashboards, will host the machine learning pipelines, and so on. So if we were to compare the technologies, I would focus on LoRa and NB-IoT since Sigfox lately has been out of the market. So LoRa operates in the unlicensed spectrum, meaning that one can procure their own access point, deploy their own system, and operate their own network, whereas NB-IoT operates in the licensed spectrum. Therefore, a mobile network operator will need to deploy the system over the cellular network, and a SIM card or an eSIM card would need to be purchased for each sensing device, and a monthly premium be paid. Now, this difference, the operating in the unlicensed and the licensed spectrum, provides some advantages and disadvantages, or some differences in terms of how the network operates. So the LoRaWAN network has a duty cycle restrictions, whereas the NB-IoT doesn't. NB-IoT supports significantly higher output power levels, and therefore it is able to also support higher downlink and uplink data rates. With an onlook at the future, so NB-IoT is already part of the 5G network specification since the release 13 of 3GPP. But the 6th generation networks also provision the use of aerial network infrastructure, in particular low Earth orbit satellites, high altitude platforms, and the use of UAVs and drones. And the use of LP1 technologies in conjunction with these airborne network infrastructure is expected to provide higher capacity networks for IoT systems and the more agile and efficient ways of deploying such systems. At the transport layer, we have also dedicated IoT protocols. What is the transport layer? The transport layer is the networking layer that provides end-to-end communication services between applications. So it provides services in order to control the flow of data among end-to-end, between two ends, multiplexing and error detection. And the most common one used in the context of IoT is the message queue telemetry transport, MQTT or MQT, which is a publish subscribe lightweight messaging protocol, where the sensors generate data and annotate the data based on some topics that they publish. And then the MQTT broker deals with pushing the corresponding data to subscribers who have subscribed to the same topics. This architecture is very agile and scalable, as it obfuscates the technical details of a sensor from the subscriber. So a subscriber can pull sensory data that are of interest without the need of being aware of the details of a sensor. For instance, what is the make of the sensor, how to access the sensor, and so on. Now I will discuss the deployment cases here in Dorset. This is a joint work with the BGS landslides team that has been taking place over the past few years. So I will start with our first approach. That was to develop a system for monitoring the cliff stability at Bournemouth, of the cliffs overlooking Bournemouth Beach. So this is a landslide that took place within the urban area of Bournemouth. From geological terms, this is a very small, insignificant landslide, but the impact to the local community is very significant. And the local council actually puts a significant amount of resources in monitoring this 7-mile stretch of coastal cliffs. So our first approach was to try and provide the local council with a system that would allow them to more efficiently monitor the conditions of the cliff. So our approach was very ambitious and resulted to an overcomplicated design. So this is the schema of the sensing device that we developed. At the core lies a SparkFun IoT development platform that was interfaced with a GPS RTK2 board with the hope of being able to very accurately monitor the exact deployment position of the device. And it was also interfaced with a geophone over 2 amplifiers. So the idea was that the geophone would capture some activity taking place on the cliff, and it would wake up the device on demand, and then the device would very quickly sample the exact location, its exact location, and hopefully capture any soil displacement. So the LP1 considered was Sigfox because at the time the Bournemouth Local Council was deploying a Sigfox network in the area. And we did a detailed evaluation of the operation, in particular of the operation of the device, and in particular the lifetime of its battery. And however, this is a bit tricky because it doesn't take into consideration the power drawn by the geophone. So the 600 days provisioned battery lifetime is a bit over-optimistic. Then the second approach was in the context of the 5G Rural Dorset project. It considers the deployment at Lyme Regis and Barton Bradstock, where we switched to an Arduino Nano 33 platform because of the greater support that this board has in terms of its firmware and the libraries. And here we trialed the use of 5G NB-IoT technology provided by Vodafone. So the architecture of the system was the typical one for an LP1 network, IoT devices deployed at the face of the cliff, transmitting sensory data to the local mast, Vodafone mast, and from there to the IoT cloud server of Vodafone, and from there over RESTful APIs over to data analytics and data visualization boards, dashboards hosted on AWS. The modalities that were monitored included the use of distance at cracks and gaps on soil. So these were monitored with the use of ranging sensors using laser, mini LiDAR, and ultrasound technologies. Also soil displacement was indirectly detected by the use of a 6-axis digital accelerometer that monitored the device orientation in space. Now the devices were developed and deployed, but unfortunately the NB-IoT trial failed, and this was mainly because of issues with the mobile network operator providing the service at that area. However, lessons were learned with regard to the design of the devices. So in a new use case at West Bay in Bridport, we simply switched to a different technology, now from NB-IoT to LoRaWAN. And we simplified the design in order to extend the battery lifetime. And now we're focusing on the device orientation in space by the use of digital accelerometers and soil temperature. Now, with the use of LoRaWAN, we had to develop and deploy our own network server. However, the challenge now that we're facing is that due to the geology, to the topology of the deployment area, the access point is deployed at a lower height than the actual end devices, and therefore the line of sight is not ideal, and the devices are having an issue with communicating data and maintaining a stable connection to the access point. So additional devices that we will deploy, we will revert back to NB-IoT, because in the meantime, network coverage has been provided to that area as well. And finally, we are in the process of deploying devices for monitoring sand drains, again back at the East Cliff location in Bournemouth. So across the entire 7-mile stretch of the coastal cliffs, the local council has drilled more than 700 sand drains. That is boreholes that are perforated, and they allow water to seep through and be removed away from the cliff, therefore defending its stability. However, these boreholes were firstly drilled like 25 years ago, 30 years ago. And in the meantime, the council is not fully aware of how effective they are in draining away the water. So in order to clear and maintain each individual sand drain, this incurs a cost of £5,500 for the entire 700 of those to be maintained. That is, to use specialized vacuums in order to remove debris and clear the pipe. Around 5 million, more than £5 million cost will be incurred to the local council. So developing an IoT system that will be able to be deployed rather easily and monitor how the rate at which each sand drain drains water away from the cliff will inform the spending of this 5 million. So I'm aware of time. I'll try to speed up. So in order to develop this device, we had to repurpose an optical flow sensor that has initially been designed in order to provide speed and direction data to drones. So essentially, this is a camera, an optical sensor that is able to detect motion, that is speed and direction of travel, by taking multiple consecutive snapshots and comparing the two. And all this happens on board, on this single board. So by deploying such devices inside the sand drain, we will be able to monitor the flow of water down the pipe. So this is a work in progress. And final slide. This is the detailed architecture for collecting and storing time series data on the Amazon web server, where the use of an MQTT broker and of Lambda functions, that is functions on AWS that allow you to run a snippet of code without the need to provision a dedicated server. And this architecture is also more scalable than provisioning a regular server, as well as more cost efficient. Happy to provide more details if requested, either later during the discussion or offline. And that was it. Thank you for your attention.
Thank you, Marius. Then it's time for questions and discussions, curiosity. So who wants to, please, if you, Alex, also can also turn on the camera. I mean, as all the people attending, if they want, they can turn on the camera. I think this may help to trigger the discussion a little bit too. There are any questions? Yeah, there's one question. I think Farouk was asking a question. Farouk, do you want to make yourself?
Yeah, just a question to Alex and Francis. Have there been any more recent landslides since 2013 that you can use for kind of verification of the model early warning system you're developing?
So far, the big event was in this year, in 2013. There was another one in 2018, but it was just one landslide, one specific area. It was very local event. It's not at the magnitude as the multi-landslide that happened in 2013. That's, yeah, maybe it's not the best case for calibrating purposes of our model, but so far, at least that also helped us to improve the model whole. As I mentioned, we already have a couple modeling, but we have the problem that we calibrated only for one event, and then when we're trying to estimate for another event or for another date in which has similar precipitation, accumulated precipitation event, we're getting also similar response. So the model is providing landslide what they weren't. And we are now working on that. We are trying to maybe change the infinite slope approach we're using, also exploring some machine learning techniques. But yeah, this is something that I mean, I wish I had more data to validate, but so far we are not. And you also mentioned in your question something about a threshold for the early warning system. We've found actually, as I mentioned in the presentation, we consider one snow component in the modeling. If we take only the precipitation time series that we have in the station, we don't see this peak, or we cannot differentiate the event of 2013 from the other events. But if we take the result of the snow model, which is the rain plus snow melting, and we accumulate this time series each 7 days in a mobile window, we can see a peak which differentiates a lot from another precipitation events that happen later. So this is something that it wasn't performed before. This is something new in our study area. By using this snow model, we now can actually set a threshold considering this new time series of the rainfall plus the snow melting. All this is new. We recently found it in the last month. We're still working on it and how to implement this in our couple modeling to improve the representation of the landslide susceptibility.
Okay, and my other question is about the terminology you're using. You're using landslide susceptibility, but I mean, usually, when we look at the landslide hazard, the susceptibility factors refer to the static factors that are not changing, whereas the triggers refer to the dynamic factors like rainfall or earthquake trigger and so on. But it seems to me that the way you're using susceptibility is that when you're getting a lot of rain, then some areas become susceptible, while other things are not susceptible. So we have to be a little bit careful about, the terminology, not to get confused. So could you explain what you mean by susceptibility?
I know what you mean there. Still, even for me in the beginning was a bit confusing, which is susceptibility is the hazard or not. Let's say so far we are, when I refer susceptibility, I mean the initiation areas of landslides, at least from my understanding. If I want to talk about hazard, I should go further and talk about the runout process of these initiation landslide areas and which areas are actually affected. And that's what I understand so far about these both terminologies.
Okay, we can have a discussion about that later on. Thank you.
Yeah, sure.
Other questions or curiosities? I do actually have for you, Alex, but we don't want to have an exam.
Okay,
but it's just a simple question: how you are using the monitoring sensors into your IoT? I'm not sure I got it exactly. So how you are using the monitoring sensors data into your regional model?
Mm-hmm. And one of the schemes I present was this prototype early warning system. The first component was related to data collection. So far, we are working with the automatic station from the local meteorological network. So they release near real-time data every day, hourly data. So far, we automatize the process of extraction the data from those sources to fit the model. This is still a work in progress. We so far have developed the codes, but we are for now only working with the local data, and also maybe Francis also can explain better this from the MeteoBlue platform for the forecasting. Forecasted data from 6 hours, 24 and 48 hours. That's what you meant, Luca? Or?
Yeah, no, because we are also finding issues in kind of using some local measurements into a regional system and local measurements of volumetric water content, for instance. If from one side is kind of straightforward to use rainfall data, on the other hand, into a physically based model, on the other hand, using like water content, point measurement of water content into a physically based model, this is a bit more tricky to define, right? To understand.
Well, yes, so far to fit our model, we only require temperature and precipitation. We are installing new sensor of volumetric water content. We only have one so far. We're trying to install new ones in where there are already one station installed and another one where there is nothing. But the volumetric water content for us is more about validate our hydrological model. We are not using it as an input.
Okay, thanks. Yeah, other questions?
I'm
Yes.
Cristiano from ANAS, Italy. I have a question for the first speaker, always about the real-time measurements. Do you assess the quality of the MeteoBlue prediction forecasting based on the measurement of the rain gauge?
I think, Francis, you can answer that question.
Yeah, we select the points of the optical to MeteoBlue, where we these points in this point we have rain gauge, and we compare it for about last 3 or 4 months. The data provided by MeteoBlue and the data that we collect from our rain gauge.
This is what you wanted to know, Cristiano, or you have a kind of following up question?
Actually, I didn't really understood the answer. However, I try to repeat the question. If you use the rain gauge to validate the forecasting of MeteoBlue, I mean if you have a period of time sufficiently to do this, a number of events to do this, and in this case, if there is a coherence, a congruence between forecasting and real measurements.
Yeah, we consider that yes, because we have hourly measurements from the last 4 months, and we compare the data collected by the rain gauge and the data provided by MeteoBlue forecast, and there are a lot of correlation. Maybe it's it differs a little bit in the measurement, but not in the tendons.
Okay, thank you.
Thank you.
Christian, please go ahead.
Yeah, thank you. Yeah, I'm Christian from the British Geological Survey. I thought a question for Mino. First of all, thank you very much for reminding us about early warning systems. I mean, we're working and also in the working group with Graciela about operational early warning systems. And I think just showing this definition again is really important because I think quite often this is forgotten. The question is more in your local example, you showed there's a railway line at the bottom. Is the railway provider in any way included in this whole process, especially if it goes then from forecasting to warning and so on and so on? Or is it just at the moment not at this stage? Thanks.
This started, as far as my understanding, maybe Loka can answer it better because this project started before I joined here. And the starting point was along with the railway, but later on, now we are doing this only within NGI. This is not related to the railway provider. That's why we do not have a very organized response part. We are getting SMSs within NGI, but this is not related to the asset owner. That's why we do not call it as an early warning system, operational early warning system. Yeah.
Yeah,
Okay.
actually, if I may add on top
Yeah.
of that is that the project and the case study at the slope scale, it started because the railway line wanted to double the line. And they were a bit worried about these steep slopes that were along, the path. So they were installing some sensors back in 2016, and then they were checking also if the slope were moving with inclinometers. And then they did geotechnical in situ investigations. And then they went for some structural mitigation measures at the base of the slope. So this slope is and that's the reason why we are focusing our attention on the topest part, which is the steepest one, because at the entire slope, they put a butterfield material at the toe, so they had kind of stabilized it. But still, the upper part is very steep, partially saturated conditions, susceptible to kind of fast slope movements or translational movements. And so everything started as a research activity, and with the aim of proving that we were able to provide this kind of this tool, this kind of stability analysis in real time. So it's a kind of prototype. And at the moment, the warnings, so the messages, it's just internally. We receive these emails as soon as the factor of safety of one of the two machine learning regression models are going below 1.5, or when one of the hydrological variables monitored, like water content at 6 different depths or pore water pressure, are exceeding 1 in terms of standardized measurements, right? If they are exceeding 1, it means that they have never been so high in the past 1 year. That's the thing. So this is what we are doing. That's the reason why it's not an operational early warning system. It's a prototype. It's a real-time slope stability analysis. Yeah.
Fantastic. Thank you.
You're welcome. Other questions or curiosity? About anything? I actually do have another curiosity for Alex here. In the hydrological model you have used, is this like the infiltration equal to the rain, or is infiltration equal to rain minus evapotranspiration or something like that?
Yes, I show a very simplified scheme of the hydrological model, but as you mentioned, there are losses by evapotranspiration. Also, the infiltration methodology is based on the variable infiltration curve, which is basically a potential or exponential formula which have 2 or 3 parameters, which are derived from some soil properties. Using this equation, split the water, which go as a runoff directly, and the remaining to infiltration, which fits the one main reservoir which represent the soil layer. Then there is another process to split this the water, the runoff, based on the saturated hydraulic conductivity from the Ortonian approach. If it's greater or less, it goes directly as a fast flow or as a slow flow. This is more or less the complete scheme. It's a very complete model. The CREST model is already used in the flood early warning system in US. We do a lot of research to choose which hydrological model is more suitable for us, because, as you know, if we work as a physically based, usually it requires a lot of parameters, which we don't have. It requires also a lot of computational cost. That, okay, somehow we can try to buy a good computer and so, but so far we tested in the beginning, very beginning, before starting everything, this CREST model with another models. We found out that this is fast and require, in comparison with another one, less parameters. And well,
so is this CREST model that has also this evapotranspiration? Is this one that you are using now, right?
Yes. You actually you insert the evapotranspiration as an input also.
Okay.
So you can estimate it based on the temperature and get those.
Okay, thanks. Other questions before closing, or curiosities or comments? Yeah, Christian, please.
Just a quick one, Marius. Maybe you can explain us this better. When I worked with wireless sensor networks. Now everybody calls it IoT. Is it the same? Is it a mixture? Is it just another word? I mean, you showed the different things. I don't know. Could you maybe enlighten or tell us? Is it, what is the difference? Wireless sensor networks and IoT.
Sure, Christian. I would say that wireless sensor networks was a paradigm where the devices were able to communicate with one another in close proximity, mainly. So it required to have multi-hop routing propagation of data towards a local base station. And from there, it would go to the outside world or to another computing system that is more powerful. Whereas in Internet of Things, the interconnection is more ubiquitous. It's for instance, in NB-IoT, the devices are able to communicate directly to the mast, the local mast of the mobile network operator, in the similar way to our smartphones. So the provisioning of the system is much simpler. Also, the technologies are more efficient now in terms of energy, more affordable. So the systems provisioned are at different scale and more easy to deploy, I would say.
Fantastic, thanks.
I have a follow-up actually about that, because when I saw the definition that Marius, you were proposing about IoT, it's nice. It's nice. It was nice to see from my side that you were focusing mostly on the kind of some characteristic of the instruments you install, right? That if they need to be low cost, they need to have this and that. From maybe a geotechnical point of view or a geotechnical, geophysical, geologist point of view, you may focus mostly on, like the definition is mostly kind of real time getting data and use this data in real time in a model to kind of have some information about something, right? In this case, since we are speaking about landslide, something about landslide. So it's this procedure of getting data, using the data in real time with a model, and then providing some output in a real time way. So it's more focused on the procedures, I would say, on the use of the technologies. But it was nice to see also kind of a definition focusing on the instruments, on the instrument itself.
Actually, Luca, your comment is relevant, because even for IoT systems, the trend over the past few years is that they become increasingly data-centric. So having solved the fundamental problems of communication, particularly with introduction of LP1s like LoRaWAN and NB-IoT, now IoT devices are able to transmit, that is battery operated, highly constrained embedded devices are able to transmit data over very long distances for extended periods of time. So having solved that basic fundamental problem, now increasingly the systems are becoming more and more data-centric. And what I didn't mention was also the trend of deploying machine learning models natively on such devices, whether it is in order to increase the accuracy and precision of collected data. For instance, when we're dealing with digital accelerometers, the noise to signal ratio tends to be really high. So we may have machine learning models running natively on the device in order to improve the quality of the collected data. So that dealing with the data is definitely part of the equation here. But for instance, a contradiction would be if we have a Raspberry Pi that, in order to operate for 2 weeks, needs to be powered by a car battery. I wouldn't regard this as an IoT system in the sense that it violates the ubiquity and the pervasiveness that the paradigm provisions. So if we were to deploy 700 such devices, would we need 700 car batteries and just to run for a couple of weeks? You see, that's where I believe the differentiating factor comes in.
Yeah, I think it's a good point of view and clarification about these things. Other comments or questions from you others? Otherwise, we can just close. I need to thank the speakers, Mino, Alex, and Marius, and of course all the people that have attended this meeting. And thank you very much. This recording will be available. Share with the Landwehr community for sure, so you can find it on the website. Thank you very much. And if you want to be informed and updated with the activities, just go on Landwehr and subscribe, and you will be added to the mailing list and be informed about the activities. Thank you very much. See you soon.
Thank you, Luca. Thank you, everyone.
Thank you. Bye.
Have a good afternoon.